Good evening students. In this video we are going to learn about the page replacement algorithms. There are various page replacement algorithms available in the operating system as listed here. First in first out page replacement algorithm, optimal page replacement, least recently used page replacement, second chance algorithm, and counting algorithms. Under counting algorithms, least frequently used algorithm, most frequently used algorithm is available. When is the requirement for the page replacement in operating system? A page fault occurs when the required page is not available in the physical memory. In this example, we see that the page table maintains the list of available frames. If the page is available in the physical memory, the corresponding bit is valid. If the page is not available in the physical memory, the corresponding bit will be marked as invalid in the page table. So when there is a reference for a specific page whose reference bit is invalid, then a page fault occurs. Assume that here a page fault occurs for the page number 0. So immediately the memory management unit identify a victim page in the physical memory and it is replaced by the required frame from the secondary storage. So how do this memory management unit identify the victim page? This identification of the victim page is done with the help of various page replacement algorithms. First I am going to discuss about the first in first out page replacement algorithm. In this algorithm, assume that we have a reference string. This reference string is nothing but the list of references to the page numbers accessed by the process generated by the CPU in this order. Assume that there are 3 frames are allocated for that particular process in the main memory. Initially, the 3 frames are empty. So when there is a reference for the page number 7, a page fault occurs and it is immediately loaded into the free frame in the physical memory. Next, a reference to the page number 0, a page fault occurs and 0 is loaded in the next available free frame in the physical memory. 1 is loaded into the next available free frame in the physical memory. When it comes to the page number 2, there is no vacancy in the physical memory, so therefore target frame is to be identified for replacement. According to FIFO concept, the first page is 7. 7 is the target page for replacement by page number 2. So therefore 7 is replaced by 2. So the next required page is 0. 0 is already in the physical memory. There is no page fault. So 3. There is a page fault for 3 and the next page to be replaced is 0. 0 is replaced by 3. Next reference frame page is 0. 0 is not available in the physical memory. Page fault occurs and the next victim page is 1. 1 is replaced by 0. The next reference page is 4. 4 is not available in the physical memory. Page fault occurs. According to FIFO concept, the target frame is 2. 2 is replaced by 4. So in this way, the pages are replaced according to FIFO concept, and according to this concept, there are 15 page faults occurs in the FIFO page replacement algorithm. The fact that which we observe in this FIFO page replacement is that when we replace a frame, when we replace a frame with a page, and that page replaced page is immediately required in the near future. So having that point in mind, we are not able to hold that page in the physical memory, because according to first in first out concept, the first frame entered into the physical memory has to be replaced by the requested frame. So therefore in this way, so the more number of page faults occur in the FIFO page replacement algorithm. So that is the disadvantage with the FIFO page replacement algorithm. Suppose if we increase the number of frames allocated for a particular process, can we reduce the page faults? To analyze this, we are testing the performance of the FIFO page replacement algorithm for the given reference string by changing the number of frames from 1 to 7. When the number of frames are 1, the page faults are 12. When the number of frames are 2, the page faults are, there is no reduction in the page faults, 12 only. When the number of page faults are 3, the number of page faults are 9. And it is observed that when the number of frames in the physical memory is increased to 4, but there is no reduction in the page faults. In fact, it is increased to 10. This increase of page faults by increasing the number of frames is called as Biletti's anomaly. Therefore, from this we can conclude that there is no guarantee in the reduction of the page faults even if we increase the number of frames in the physical memory for a process. Next page replacement algorithm is optimal page replacement algorithm. According to this algorithm, the pages required in the future are kept in mind before replacing a page in the physical memory. Initially, there are three frames available for the process in the main memory. So initially all the three frames are empty. When there is a reference for page number 7, frame number it is occupied in a empty frame. Page fault occurs and it is occupied in an empty frame. Next, reference to page number 0. It is occupied in a next available empty frame. Reference to page number 1. Page fault occurs and it is occupied in an empty frame. The next required page is 2. But 2 is not available in the physical memory. Page fault occurs and there is no free frame for accommodating this page number 2. So we have to select a victim page for accommodating the page number 2. So therefore what we do according to optimal page replacement algorithm is we refer the pages which are required in the future. So 0 is required in the near future. So 0 is not the victim page. Next 3 anyway not available. Next again 0. 4 anyway not available. 2 is the next page referred in the future. So therefore, 0 and 2 do not be taken into account for page replacement. Therefore, according to this optimal page replacement concept, the next victim page for replacement is 1. So the 1 is replaced by the page number 3. So 1 is replaced by 3. Next required page is 0. 0 is anyway available in the physical memory. There is no page fault. So when there is a reference for page number 4, page fault occurs, then we need to identify the victim page for replacement. So 2 is the next immediate required page. So 2 is not the target page. 3 is also not the target page because it is requested immediately. So therefore, 2, 3 are safe and 0 is the next page replaced by 4. Next, reference to 2 and 3 do not cause any page faults, and again reference to 0 causes a page fault. So therefore, optimal page replacement algorithm look ahead for a target page. So 3 is required, 2 is required in the near future. So 3 and 2 are not victim pages. So the only page left over is 0. So 0 is replaced by the next page. 0 is replacing the page number 4. Like this the process continues, and the number of page faults in this optimal page replacement algorithm are 9 page faults. It is better than the FIFO page replacement algorithm. Coming to least recently used page replacement algorithm, this is the reference string, and initially there are 3 pages, there are 3 frames available for the process. All the 3 frames are initially empty. So when there is a reference for page number 7, a page fault occurs and 7 is loaded into the free frame. 0 page fault occurs, loaded into the free frame. 1 page fault occurs, 1 is loaded into the free frame. So when there is a requirement for page number 2, we need to identify the target frame for replacement. So in this least recently used algorithm, we look back the previously accessed pages. So according to least recently used algorithm, we have to select a page that is least recently used. So one is most recently used page, so therefore one is not the target. After 1, 0. 0 is also not the target. After that 7. So 7 is the least recently used page compared to 0 and compared to 1. So therefore 7 is the page becomes the victim page for replacement by page number 2. Next, anyway 0 is available in the page in the physical memory, no page fault. 3 not available in the physical memory, so page fault occurs for 3. So to replace 3, so we again refer the list of pages accessed previously 0 to 1. So 1 will become the target page for replacement. So 1 is replaced by 3. 0 is the page available in the physical memory. 4 is not available in the physical memory. Page fault occurs for 4. So when we refer 0 most recently, after that 3, then before 3, 2 is the page used. According to least recently used concept, 2 is the least recently used page. So 2 will become the replacement for 4. When we refer page number 2 again, page fault occurs. So according to LRU, 3 will become the target frame for 2. 3 is replaced by 2. Next, 3 is the reference page. 0 will become the target frame for 3. Then again 0 is requested. When we look back, 4 will become the target frame for 0. So 4 is replaced by 0. 3, 2 are available, no page faults. Coming to 1, look back, 2, 3, 0. So 0 will become the page replacement for 1. Then 2 is available already, no page fault, 0. So for 0, when we look back, 2, 1, 3. So 3 will become the replacement for 0. Then again 1 already available in the physical memory, 7. So when we want to accommodate 7, look back, 1, 0, 2. 2 is replaced by 7. Then 0 already in the physical memory, 1 already in the physical memory, no page faults. So totally the total page faults in this least recently used algorithm is 12. Next algorithm is second chance algorithm. According to second chance algorithm, a reference bit is maintained by a page table for each page stored in the physical memory. When a page is brought into the physical memory, its reference bit is marked as 0, and when the page is referenced by the CPU, then the corresponding reference bit will be turned to 1. So likewise, the reference bits for various pages will be 0 and 1 according to the usage, and when it is brought into the main memory, it is 0. When it is used, it is 1. Second chance algorithm, when it finds for target frame for page replacement, it will look out the reference bits for each and every page. When the reference bit is 1, it indicates that the page is used recently, and we would like to give a second chance for that algorithm, second chance for that particular page. So 1 is replaced by 0. In that way, the reference bit for that particular page will be turned from 1 to 0. Similarly, the next frame is checked in the physical memory. If the next frame is again occupied and the reference bit is 1, it is turned into 0. If the reference bit is 0, it indicates that the page is brought into the main memory but it is not referenced. So therefore, this 0 bit indicates that the page can be replaced. So according to second chance algorithm, the page with 0 bit will be replaced. Likewise, the algorithm will continue in identifying the victim pages for page replacement. Let us look into the example for a second chance algorithm. Assume that the list of pages referenced is in this order 0, 4, 1, 4, 2, 4, likewise up to 3, 4. Assume that there are 3 frames allocated for the process. Initially 0 is the referenced page. So 0 is not available in the physical memory. Page fault occurs and 0 is loaded into the free frame. When a page is loaded into the physical memory, the reference bit for that particular page is marked as 0 and is stored in the page table. Similarly, 4 is brought into the physical memory, its reference bit is 0. 1 is brought into the physical memory, its reference bit will be marked 0. Now, 4 is referenced. When 4 is the page accessed, the corresponding reference bit of that 4 becomes 1. Next, 2 is accessed, the corresponding page is not available in the physical memory, so therefore we need to identify the victim page. So we start from the beginning. So when we start from the beginning, this 0 indicates this page number 0 is brought into the main memory but not accessed. So therefore this page is replaced by page number 2. Next one, page number 4. 4 is available in the physical memory and its reference bit is 1. So 1 remains 1. Next, coming to page number 3. When there is a reference for page number 3, 3 is not in the physical memory, therefore page fault occurs. We need to identify the target page and the pointer is pointing to the second frame. The reference bit for the second frame is 1. That indicates that the page is recently accessed, therefore it is 1. So the second chance algorithm will give a second chance to this particular frame and the corresponding entry of that particular page in the page table is turned from 1 to 0. So therefore we are giving a second chance to page number 4 by converting its bit from 1 to 0. And next, when we search the next entry in the page table, next entry in the physical memory, 1 is the next available entry in the physical memory. The corresponding bit for the page number 1 is anyway 0. So therefore this page is the target page for the replacement. So 3 is brought into this location. After 3 again page number 4 is referenced. So when page 4 is referenced, so the corresponding reference bit is turned from 0 to 1. Next 2 is accessed, the corresponding bit will become 0 to 1. 4 is accessed, so 1 remains 1, reference bit 1 remains 1. 0 is accessed, so 0 is not available in the physical memory and we need to identify the target frame for the page replacement. And the pointer is pointing to the first entry in the physical memory and the first entry page is 2 and its reference bit is 1. So 1 is not the victim page. The reference bit 1 is turned to 0 because we are giving the second chance for the page number 2. Next available entry is page number 4. The reference bit of the page number 4 is also 1. So 1 indicates that it is not the victim page. So we are giving a second chance for that particular page. So 1 is turned to 0. And the next page identified is page number 3. Page number 3 reference bit is 0. That indicates that this is the target frame for page replacement. So likewise page number 3 is replaced by page number 0. And when page 0 is brought into the main physical memory, the corresponding reference bit of 0 is marked 0. In future, if this page is referenced, 0 is referenced, then the corresponding entry will be marked 1. So now you see when page 4 is referenced again, the corresponding reference bit will be turned to 1. That indicates that we are going to give a second chance for this algorithm again. So page number 1 is not in the main memory, so we need to replace a page. Now the pointer is pointing to page number 4, but the reference bit of page number 4 is 1. So therefore the target frame for replacement is not 4. The bit 4 will be replaced by 0. 1 is replaced by 0 and the next target frame will become 0 for the replacement. So likewise the procedure continues until all the requests are processed. Enhanced second chance algorithm maintains a pair of bits. The first bit is called as reference bit, second bit is called as a modify bit. If the reference bit is indicating 0, means the page is just brought into the main memory and not yet been accessed. And when the reference bit indicates 1, means the page is brought into the main memory and is accessed recently. So that is the meaning of the reference bit 1. Modify bit indicates whether the page is modified or not modified after brought in from the secondary storage into the main memory. So modify bit 0 indicates that the page is clean and is not modified. Modify bit 1 indicates that the page is modified, and when it is the replacement for some other page, then this modified page should be written into the secondary storage. In this combination 0, 0, that indicates that the page is neither recently used nor modified. So this is the best page for replacement when there is a need for the selection of the target frame. 0, 1 indicates that it is not recently used but modified page. So when this page is the target for page for replacement, then this page must be written into the secondary storage for saving the changes. 1, 0 indicates that this is recently accessed page but not modified and it is a clean page. So therefore when this page is the target frame for replacement, then this page need not be written into the secondary storage because it is already clean. 1, 1 indicates that it is recently used and is also modified. So therefore when you want to replace this type of page, then it should be stored into the secondary storage for saving the changes. So the order of preference for page replacement is, first we look up for the 0, 0 combination, and if it is not available, then we will look for 0, 1 combination of pages, and if it is not available, then we try for a page with the reference bits 1, 0. If it is not available only, we will try to replace a page whose reference bit is 1, 1. This is the order of replacing the pages. Preference order of the replacement of the pages in the physical memory when there is a need for the target frame to identify. Next algorithms are counting algorithms. There are two types of counting algorithms: least frequently used algorithm, most frequently used algorithm. Least frequently used algorithm means the page table will maintain how many number of times the page is referenced. That count indicates if the count is higher in number, that page is used more frequently. If the page count is less in number, it indicates that the page is less frequently used. Least frequently used algorithm replaces a page with the smallest count. That indicates that this page is less required in future. That is the assumption made in this least frequently used algorithm. In most frequently used algorithm, a page with largest count will be the target frame. That indicates that the page is already used so many times in its history, so therefore that page may not be required in future. That is the assumption made here in most frequently used algorithm. So therefore the most frequently used algorithm replaces a page with highest count number as the victim page for page replacement. So in order to save the time for the operating system to identify the victim page for page replacement, the operating system can follow these techniques, that is page buffering algorithms. According to page buffering algorithms, the first method is maintaining a pool of free frames always. This indicates that when we maintain a pool of free frames and when there is a requirement for page to be loaded into the physical memory, then one frame from the pool of free frames are selected and that frame will be allocated for the new page that is coming into the physical memory. And after this, when the operating system will identify a target frame from the list of available frames in the physical memory, and it will empty that frame, and then it will again send the empty frame to the list of free frames. Here the idea is the operating system do not want to waste its CPU time in waiting for identifying the victim frame for page replacement. The victim page is identified after the page is replaced by taking a free frame from the pool of free frames. That is the idea behind this keeping the pool of free frames method. Next one is keep list of modified pages. So when there are modified pages in the physical memory and the backing store is idle, to save time, the modified pages are written into the backing storage so that the corresponding entries regarding the modification of the pages in the page table are set back to clean status, so that when the pages are in the clean status and when it is becoming the target for page replacement, then there will not be any requirement to store that page in the secondary storage. Simply the page can be replaced by the required page in the physical memory. In this way, the time can be saved by identifying the modified pages and writing the first pages when the backing storage is idle. In its free time, the modified pages are written into the secondary storage and the corresponding entries for that pages in the page table can be set to clean status. In this way, page buffering algorithms help in reducing the CPU in reducing the CPU idle time by maintaining a list of free frames and also the list of modified pages methods. Thank you for watching this video.